Good evening, class. Well, actually, hi, class. This is Mr. Collier. Uh, Today, we're going to be talking about intersections of circles and tangent segments. So, my teacher for the day, if you have not done so already, go ahead and pass out the assignment that goes along with it, the notes page. Students, please make sure you take good, careful notes, as these notes, just like the ones that you took last week, will help assist you in the assignments that are to come. I will be sending some assignments for you to work on during Anchor Day Wednesday and also on Thursday. So please make sure that you take good notes. Also, please make sure that you show your work with these problems. So let's go ahead and get started. So today we're going to talk about what I call party hat problems. And the reason we call them party hat problems is because if you look right here, you see that it looks like a party hat. All right, it looks like a party hat. And so what we're saying is that we've got two segments. So if we have two segments that are coming from the same exterior point, meaning if it's a point S right here, and we got a segment that's coming, got two segments that's coming from that same exterior point or exterior vertex, whichever way you want to call it. And those two lines or segments are tangent. Remember, tangent means touches the circle at one spot. So that means that it touches the circle here and it touches the circle here. Then basically what we're saying is that those two segments are equal to one another. They are congruent. But once again, the reason we call them tangents, or I call these party hat problems, is because if you think about it, if I put a little face right there, then it looks like a party hat on top of a head. So let's look at the first problem. So I'll give you a chance to copy the problem down, and then we'll go through and work the problem. All right. So if we're talking about solving this problem, basically what we're saying is that I've got this external point, and with this external point right here, I've got two line segments that are coming from it. And remember, these are both what we call tangents. And since these are tangents, that means that I can actually just set them equal to each other. And so when we set them equal to each other, of course, please make sure you remember that right here, of course, I'm going to subtract 4 from each side, and that gives me a 3x is equal to 12. And then when I divide both sides by 3, notice I get x is equal to 4. And so a way to check yourself is just to plug it back in to make sure that they equal one another. And so when I plug it back in, of course, I get 3 times 4 plus 4, which is basically saying 12 plus 4, which is equal to 16. So we see that it does work. Let's look at the second one. I'll give you a couple of minutes to copy that down. All right, just like with the last problem, remember the key is setting the problem up. On the last test, what I saw from a lot of you is you're not setting the problem up. You're not asking, you're not going through the process, and you have to make sure you trust the process. The process states that in this particular case, we have a outside point, and we have two segments that make tangents with the circle. So in that case, we set them equal to each other. Then we'll subtract 2 from both sides and we end up with this. But remember, your goal is to get x by itself. So therefore, what I do is I actually take the square root of both sides. And now look what we get. Now the reason that 3 and -3 both work is because if I take -3 and plug it in, -3 squared plus 2, that gives me positive 9 plus 2, which is 11. And then even if I plug in positive 3, I get still 9 plus 2, which gives me 11. And we see that it does work out. Let's look at number 3. So when I look at number 3, and I know some students, when they look at this one, they'll say, well, Mr. Collier, this one has an x and that one has an x squared. So that means I do something different. Well, no, the same process applies. We've got an external point. We have two line segments that are tangents to our circle. Nothing's different about this particular problem. We set it up the same way. But now let's look and see what we have. Well, we have a squared term and we have a single x term. Well, anytime you have this, you set everything equal to 0 and you want to put everything on the same side. So what does that mean? That means that I'm going to actually take my 14x and move it across the equal sign. Now remember, whenever you bring something, whenever you change sides of the equal sign, remember, changing sides of the equal sign means changing signs. And so we end up with this. Well, now this is back to some factoring. And basically we're trying to figure out, well, there are factors of -15, because this is a -15. And I'm trying to see what factors of -15, when I take the sum, will give me a -14. And that's because of that. So when we think about the factors of -15, well, I've got a 1 and a 15, I've got a 3 and a 5. Well, remember, we want -14. And since we want -14, that means that my larger factor has to be negative. So now when we look at this, we ask ourselves, well, okay, what is 1 times -15? Well, that gives me -15. But 1 plus -15 gives me -14. Of course, 3 times -15 gives me -5, gives me -15. But when I add these two, I get a -2. So we see this one does not work, and the only one that works for us is a negative, is +1 and -15, right? And so when that happens, we set it up as this. But now we also have to make sure we remember that I have to set both of these equal to 0. And when I set them equal to 0, that means that I get x is equal to +15 and x is equal to -1. Well, when I plug in -1, I get 14 times -1, which is -14. And we've always said length is always positive. So therefore, I know -1 can't work. But when I plug in +15, 14 times +15, will give me a positive answer. All right, and I think it gives me a 210. And then when I do 15 squared minus 15, that gives me a 210. So therefore, we see that 15 is our actual answer. Let's look at number 4. All right, so when we look at this one right here, a couple of things we need to ask ourselves. Once again, do I have an external point? And I have two external points actually. All right, notice I've got D, which is an external point, and I have B, which is an external point. And so since I have an external point and I have two lines coming from each point, well, I should see that if this is 4, then I know that this has to be 4 as well. And just like up here, if this is 3, then this one has to be 3. And so if that's the case, the problem says find the value of x. Well, finding the value of x is just basically saying what is the length of BD. So when I ask for the length of BD, I get 3 plus 4, which gives me 7. Let's look at this one, number 5. Well, when I look at this, you should see that SR and QR are coming from the same external point, so therefore they're equivalent or congruent. I also see that NS and NT are equivalent, but in order for me to find NT, I need to know what NS is. And if you notice right here, notice that this entire side from N to R is 12. So therefore, if I were to do 12 minus 8, notice that gives me 4. Well, if NS is 4, that means that NT also has to be 4. And then if I look down here, PQ is 10, and since PQ and PT both come from the same point, that also means that PT has to be 10. So the problem says find the length of NP. That means that I'm going from here down to here, which basically means that I'm saying 10 plus 4, which is equal to 14. Let's look at the next one. It says, we got a point of tangency. We talked about a point of tangency back in Unit 4A a little bit. We said that if we have a point of tangency is basically the point where my tangent line touches the circle. Now, we also need to make sure we understand that if I have a radius that touches my tangent line, then it automatically creates a perpendicular with that tangent line. Now, I want to make sure you understand that one radius can only touch one tangent line at a time. One radius cannot touch two tangent lines. Now, if we had a diameter could touch a tangent line over here and a tangent line on this side, but one radius for one tangent line. Now, what we're saying right here is that it creates a perpendicular, and we said that a perpendicular is when two lines that intersect and create 90-degree angles. Well, ladies and gentlemen, if we create a 90-degree angle, guess what else we can create? We can also create a right triangle. And here we go with some Pythagorean theorem problems. So let's look at number 6. Give you a chance to copy that down. So if we notice right here, what we're saying is that we have a tangent line. So we can say AB is tangent. It's a tangent line. We can say that, let's just call this circle C. We can say AC is a radius. And remember what we said? We said that if we have a tangent line and a radius, then that means we automatically have a right angle, or they're perpendicular. So if we label everything, well, we know that this side, AC, represents one leg, AB represents another leg, and CB represents the hypotenuse. So if I'm using the Pythagorean theorem says that I can do leg squared plus leg squared equals hypotenuse squared. When I plug in what I am given, I end up with this. And so we'll look at this as being 81, 144. 81 plus 144 gives us a 225. And remember, I have to take the square root of both sides because I need to find out what x is. And so therefore, I end up with x is equal to 15. Let's look at the next one, number 7. Give you a chance to copy that down. All right, so when we look at this, the first thing we need to make sure of is we know that my radius is 12. That means that every radius in the circle is 12. So from P to R is 12. Well, from P to any point on the circle is 12. Well, that means that this right here is also 12. So that means that PQ is equal to 20. Well, if PQ is equal to 20, then that means I'm trying to find QR. So just like with the previous problem, I set it up as leg squared, hypotenuse squared. Remember that in this particular case, PQ represents one leg. Excuse me, PQ represents the hypotenuse. I apologize. PR represents one leg, and QR represents the other leg. So therefore, when I plug them in, that's basically what I'm looking for. And I know this says PR, but we can enter PR and QR are interchangeable because they're both legs, and legs are interchangeable. So therefore, we end up with this. Now, just to make sure we remember this right here comes out to be 144, and this comes out to be 400. And so when I subtract 144 from both sides, I end up with my unknown, which I'll just say is x squared, is equal to 256. And then when I take the square root of both sides, I end up with RQ is 16. So that means that RQ, this side length right here, this leg is 16. All right, let's look at the next one. Now, let me go back. I do want to make sure everybody understands that the reason I am not spending a lot of time when we go through is because I'm more concerned about some of you all setting the problem up. A lot of you all are not doing this step right here. You're not doing this step right here. For some reason, you're trying to go and get directly to the answer, and that's not helping you. So remember, I'm about setting the problem up. So when we look at this problem right here, I'll give you a minute or so to copy that problem down. All right, so let's look at it. So it says, is CB tangent to the circle? Well, what we're saying right here is that if I ask that question, is CB tangent? Well, the first thing some of you all would say is, yeah, it's tangent because it's only touching the circle in one spot. But we got some other things going on here. So I can't just say that, yes, it's tangent. I got to make sure that I prove it to be tangent. And the only way to prove when you have a radius and a tangent line, or something that we think is a tangent line, the only way to prove that it is actually tangent is to actually prove that it satisfies the Pythagorean theorem. So when we're talking about satisfying the Pythagorean theorem, we're basically saying that when I set this up, remember, this is leg, this right here is a leg, and this right here is my hypotenuse. When I set this problem up, the left side of my problem should equal the right side of my problem. So what does that mean? That means that when I do 256 plus 1024, that should give me, 832, I'm sorry. Go back. That's 24 squared is, yeah, is it? No, it's 1024. All right. No, it's not. Let me check myself. I'm sorry, everybody. Mr. Collier makes mistakes. I am human. So 24 times 24, that gives me 576. And I know that 32 squared gives me 1024. So therefore, when I add these things up, notice what I get. All right. When I do 576 plus 256, I end up getting 832. Well, 832 does not equal 1024. And since the left side does not equal the right side, that means that no, my tangent line that I thought was tangent is not tangent. Once again, when we plug it in, if the left side, once we simplified everything, if the left side does not equal the right side, then it does not mean, it is not a tangent. That's basically what we're saying. Now, if the left side equals the right side, for example, if we go back to here, right, if we go back to here and we want to do the same process, so that means that we're saying that 20 squared, because that's what my hypotenuse is equal to 12 squared plus, and we're saying 16 squared, because that's what we found our missing side to be. Well, that's saying we've got 400. This is saying 144, and this is saying 256. Well, when I add up 144 and 256, I get 400. And then on the left side, I have 400. So therefore, QR is tangent to my circle because this satisfies the Pythagorean theorem. And whenever you hear me say satisfies the Pythagorean theorem, that means basically, is the Pythagorean theorem true? All right, that's basically what it means. And we see right here, it is no. All right, so now let's look at number 9. So when we look at number 9, I give you a chance to copy that down. All right, so the first thing you should have done right here, since it's asking us to find the radius, well, that means that I need to find that and that. So let's think back to what we've been doing. We've been setting the problem up the exact same way every single time, right? We've been doing leg squared plus leg squared equals hypotenuse squared. Well, let's make sure we understand something. Leg AC is a combination of R and 16. Well, I can't say AC is equal to 16R. That is not true. But I can say that AC is equal to R plus 16, or I could say 16 plus R. Either way, I get the same answer. So now when we look at this, let's think about it. AC is a leg, excuse me, is a hypotenuse, I'm sorry. Because remember, hypotenuse is across from the 90-degree angle. AB is a leg, and BC is a leg. So now, when I set it up once again as leg squared plus leg squared equals hypotenuse squared. Same way we've been setting up every single time. And so, look what I get. Leg squared plus leg squared equals hypotenuse squared. Well, when we look at this right here, we have to make sure we understand something. I need to simplify this. So when I simplify this, this becomes R squared plus, and 24 squared comes out to be, I think we said 564. All right, well, 576, I think. And now we have to make sure we understand this. Well, understanding this basically means that when I have R plus 16 in parentheses squared, that means that I'm talking about R plus 16 times R plus 16. Well, when I do the FOIL method or distributive property right here, distributive property says that I have R times R, which is R squared. And then I have R times 16, which is 16R. And then I have 16 times R, which is 16R. And then I have 16 times 16, which is 256. Combine like terms, and I end up with R squared plus 32R plus 256. That's what we get right there. And so now, since that's what we have, now one thing you can remember is this. Whenever I have the same thing on both sides of my equal sign right here, I've got R squared on the left, R squared on the right. Ladies and gentlemen, that means that I can cancel those things out. And when I cancel them out, that means that I'm left with 576 equals 32R plus 256. Well, the next step is to subtract 256 from both sides. And when I subtract 256 from both sides, notice what I get. I end up getting what? I end up getting 320. And then the last thing is just to divide both sides by 32, and I get R is equal to 10. So that means that my radius is 10 for both of these. That means that if I ask you for the length of AC, you would be able to tell me AC is equal to 26. You should be able to tell me that AB is equal to 10. You should be able to tell me that BC is equal to 24. So that way, when I plug all of this in, right, when I decide if I want to check to see if BC is a tangent, then I should be able to plug in these three numbers into their respective spots, solve, and it should come out to be true. All right, let's look at the last one for number 10. Number 10 says, a green on a golf course is in the shape of a circle. Your golf ball is 8 feet from the edge of the green and 32 feet from a point of tangency on the green. What is the radius? Well, first of all, please go ahead and label your radius here, and your radius there with an R. Now, we need to make sure we understand something. One of my legs is equal to 32 feet. Another one of my legs is equal to R. Because remember right here, this is one leg and this is another leg. So that means that my hypotenuse, which goes from this center of the circle to this point where my golf ball is, well, that from here to the edge of the circle is R, but from the edge of the circle to the ball itself is actually R plus 8. And so now I take what I have and plug it in. So I have R squared plus 32 squared is equal to R plus 8 squared. That means that I get R squared plus 1024 is equal to R squared. We'll come right here. Remember, it's R8, R plus 8. That gives me R squared plus 8R plus 8R plus 64. That gives me R squared plus 16R plus 64. And so now I can actually just do this. Same thing we did in the previous problem. Notice since I have R squared on both sides of the equal sign, they cancel out. That means I'm left with 1024 is equal to 16R plus 64. I can subtract 64 from both sides, and I end up with 960. And now when I divide both sides by 16, I end up getting R is equal to 60. So that means that my radius is 60 feet. Well, the second part says, well, how far is the ball from the center of the cup? Well, from the center of the cup, this particular ball is not only R, because that's our hypotenuse. Not only is it R, but it's R plus 8. Well, we just found R to be 60. So therefore, we do 60 plus 8, and it comes out to be 68 feet. All right. Last thing, or a couple of things left we want to talk about. So two circles can intersect in 2 points, 1 point, or no points. Well, if a circle intersects at 2 points, that means that basically you can think about the Olympic rings, all right? Think about the top of the Olympic ring. So if I got this ring, this ring, this ring, and then I got that and that. Well, if I'm only going to use the top 2 rings right here, all right, which is basically saying that, then notice I have 2 points of intersection. Sometimes you can have 1 point of intersection, and when we're dealing with just 1 point of intersection, that means that we call them either internally tangent or externally tangent. Well, regardless, tangent means that if I do a line, it only touches the circle one time, and even though we have 2 circles, this line is touching each circle one time only. Same thing over here. Even though we have 2 circles, this tangent line is touching each one of those circles one time only. And then we can have what we call no points of intersection. Well, one of the things is that sometimes the circles will have different centers, meaning you have 2 different circles. If circles have different centers, then typically you have 2 different circles. And when we say no points of intersection, that means that those circles do not touch at all. But then we can also say concentric circles. Concentric circles have the same center, but the circles do not touch. Why? Because they have different radius, right? They have different diameter. Even though they have the same center, they have different widths. all right, or diameter. So therefore, they will never touch. Last thing we're going to talk about is surface area. So I want to make sure we remember this, all right? Surface area is when you're talking about covering something, all right? So we're talking about covering, we can say covering a ball. Well, when we're talking about volume of a sphere is talking about filling a ball with air. So let's think about the problems that you have on your paper. So one of the problems that you have in your paper says that we've got a ball, or we've got a sphere, and this sphere has a radius of 3 kilometers. And it gives us our two formulas. It tells us that for the surface area is 4 times pi r squared, and the volume is 4/3 pi r cubed. And that's for surface area and volume of a sphere. Make sure you keep that in mind. All right, surface area and volume of a sphere. Well, if my circle has a radius of 3, then that means that I can actually take the surface area formula for this and set it equal to 4 times pi times 3 squared, which gives me 4 times pi times 9, which gives me 36 pi kilometers squared. Well, what if I want to find the volume of that same sphere? Well, volume says that I can use that same radius, but now I cube it. I do 4/3 times pi times 3 cubed. That gives me 4/3 times pi times 27. And if I want an exact answer, that exact answer comes out to be 81, comes out to be 108 over 3 pi, which we know can reduce to 36 pi kilometers. And since we're cubing, we have to use cube because volume is dealing with cubes. See if you can do number 12. See if you can do number 12. I want to caution you though, when you look at number 12, it's pointing right here, but that means that the diameter is 4. Right? That means that the diameter is 4. So if my diameter is 4, then you have to work with it. You have to do something else before you actually solve it. So I hope this is very helpful for you today. Teacher for the day, please make sure if the students need to rewind back or go back to see any parts of this, they please help them do it. Really, you can just go to the screen and just press on it, and you can actually rewind it back to where they need. But they should be able to work on it with no problems. Please feel free also to take any notes down for each class period. Each class has been notified of what will happen if things are not done in accordance to how I want them to be done, their behavior and things like that. So please feel free to make notes. All right. All right, class. You all have a good day.